All right, this is going to be page 1, notes 20, Calc AB. We're going to be finding areas of regions bounded by curves. It's actually just like a really tiny extension of using the fundamental theorem. I'm going to talk a little bit about Riemann sums. So if you don't remember Riemann sums, go back and watch those videos or reread those notes, or just review a little bit, right? So we're talking about areas of regions bounded by curves. One thing that's kind of important is that when we say curve, we might just mean linear function. That's actually really common for us to say like a line is a curve. So you get over it. That's just what we do. So let's see if we can do it. So we want to find this region, which we are told is bounded by f of x, which is 1/5 x plus 3. So that's the top one. G of x, which is -1/2 x plus 1, which is the bottom one. And then 2 and 7. We had to be told 2 and 7 because they're like totally arbitrary. Like there's nothing obvious that would make a region start at 2 and end at 7 unless you were like told that. So told that, first thing we're gonna do is just approximate it with a Riemann sum, a right Riemann sum using 5 rectangles. So the key here is it's a right Riemann sum, 5 rectangles. So for 5 rectangles, what we're gonna do is we're gonna kind of like divide up from 2 to 7 into 5 equal pieces. I really hate that that is not auto-line. I'm not gonna make you watch me make rectangles here, even though I want to. So we're gonna like have 3, and then 4, and then whatever. And then there'll be wrong color, man. Okay, here we go. 5. So 5 bases. Each base is gonna be 1. 7 minus 2 divided by 5 gives us 1. So each of the bases will be 1. Now those that I just drew are not the actual bases. What's really going to happen is I'm going to draw the height of the first rectangle here, and then my rectangle. We're just doing bad rectangles. It takes way too long to like try to get them to work. That's one rectangle. For the second one, the height will be the top, take away the bottom. Then we go up here. For the next one, it's going to be top, take away bottom. Then we go over like this. If it was better at making rectangles, I would do it, but it's just not, or I'm just not. Then here, look at this, these perfectly drawn rectangles, utilizing all the technology that we have available to us. There we go, we have 5 rectangles. Now, we would need to get the area of each of them. So let's think that through. So here, let's say this height is f of 3 minus g of 3. And then the next one that we find, this height is f of 4 minus g of 4. Then we're going to continue all the way through, and then finally the last height that we're going to find is going to be f of 7 minus g of 7. So we want to generalize this, right? We're always going to be doing the base, which turned out to be 1, or delta x, times the height. Let's kind of write some stuff down. So I'm going to say that delta x is 7 minus 5 divided by 5 in this case, because we're using 5 rectangles, so 1. Evaluation points. So we always start at 2, well, we're doing 2 to 7, so it's going to be 2 plus I times delta x, so plus I delta x, so that's going to be just 2 plus I in this case. So our summation, if we write it, is going to be the sum from I equals 1 to 5, because there's 5 rectangles. If there were 10, it would be I goes from 1 to 10, of the height, which is f of x sub I minus g of x sub I. So that's the height times delta x. Let's use a calculator to get that. So I'm going to say that this is equal to, and now we'll bounce to the calculator. On the calculator, I'm going to define f of x, g of x. I'm going to type that thing in. Then maybe I'll like try it with 1,000 or something just to see what happens. Because we know that if we have more, it will be better, right? So here, f of x is 1/5 x plus 3, g of x is -1/2 x plus 1. Summation, so we're going to sum from I equals 1 rectangle up to 5 rectangles. Quantity f of 2 plus I times delta x, so I times 1 minus g of 2 plus I times delta x, so g of 2 plus 1. that's the top curve minus the bottom curve at the evaluation points, times delta x, which is just 1, so I'm going to write it, but whatever. I get 55 over 2. This is a bad estimate because 5 is like almost nothing, right? As far as the universe is concerned. What's it as a decimal? 27.5. Let's just use let's use n, right? So let's say we use n rectangles. So this is a review of Riemann sum stuff. So if you remember your Riemann sums, you'll know what I'm doing. If you don't remember, go back and watch it, right? That's why the videos exist. That's why you take good notes. So I'm modifying this to be 5 over n. So basically all my delta x's become 5 over n's. And then let's do n. So if I do n equals 5, I should get the same answer, and I do. If I do n equals 100, so I'm using 100 rectangles, I get that. If I use 1,000, I get this. Seems like we're closing in on 25.75. Like that feels like what we're approaching. But we weren't really asked to do any of that. But let's write the limit of the Riemann sum, turn into a definite integral, and see what we get. Let's go. Oh, having trouble getting back. Okay, so limit of a Riemann sum. I'm going to write the limit as n approaches infinity of the sum from I equals 1 to n of the, so it's going to be f of x sub I minus g of x sub I. And then multiply that. This is the heights. So you are heights. Height. And then times the base. So base times height, just a rectangle, base times height. This limit is going to turn into the integral from where we started, which was 2, to where we ended, which was 7, of f of x minus g of x dx. That is the definite integral. What's the advantage of this? We can use a fundamental theorem on this, right? So let's do that. So I'm gonna copy these and just bring them down for a second, and then I'll return them, or I'll delete them, I guess, when I'm done. I just need to know what the things are. So bringing that down. All right, here we go. So we're doing the integral from 2 to 7 of 1/5 x plus 3 minus the quantity negative 1/2 x plus 1 dx, which is 2 to 7. Just going to combine these. 1/5 plus 1/2 x. So 1/5, 2/10 plus 5/10 is 7/10. X squared. Oh, I'm not integrating yet. 7/10 x. And then 3 minus 1 is 2 dx. Now we integrate. So I get 7 over 20 x squared plus 2x from 2 to 7, which is going to be, all right, so let's say 7 over 20, and then 7 squared plus 14 minus the quantity, 7 over 20 times 2 squared plus 4. So that's going to be, so what I'm going to do is I'm going to combine like this with this. So there's a 7 over 20, and then I get 49 minus 4 is 45. Plus, now I'm going to combine this with this. So that's 14 minus 4 is 10. So this is 7 times 9 over 4. I'm dividing out of 5 from both of these, right? 9 over 4, so 63 over 4 plus 10 is 103 over 4, which is 25.75, which is what we thought our Riemann sums were tending to. So really good deal, right? So we don't want to do Riemann sums. Like that's sort of a general rule in life. It's like, it'd be so much easier to use a fundamental theorem when we can. So turns out finding area of a region bounded by curves is something that we can use the fundamental theorem on, and it's all based on Riemann sums. Mastering Riemann sums will make all of calculus so much easier for you. There is like an interesting thing here. One of the curves was below the x-axis and one was above. We were okay with that. Let me just delete this because I don't really need it. Get out of there. So if we have this scenario, right? And then here, so this, if we do top minus bottom, we definitely get a greater than 0 thing, like no question asked. But what if it gets more complicated? So if we have this and we have this, well here, just pick numbers, right? So like maybe this is like 12 and this is negative 30. 12 minus negative 30, top take away bottom, is still going to be, what is this, 42? Greater than 0. Top take away bottom is still greater than 0. As long as we do top take away bottom, we're going to get positives, so we're going to get our areas that we're looking for. If they're both negative, it's probably the weirdest one, and I'm using way too much space. So let's shrink some things. Here we go. Okay, what if they are both negative? This one's maybe the weirdest, but it still works. And if you're ever unsure about like a generalization, take a look at a specific thing. So maybe this is negative 5 and this is negative 30. Negative 5, the top minus the bottom, is actually positive 25. It's still greater than 0. No matter what you do, if you do top curve, take away bottom curve, the height of your rectangle is always going to be positive. You don't need to worry about where the curves reside. You just go for it. Top, take away bottom, killer. All right, so that's the end of this page. I will be back on the next page. We're actually going to do some problems. So I will see you there.